At the beginning of chapter 4, we started by reviewing the logarithms, specifically the natural logarithm, and exponential function, specifically the natural exponential function. And so in the previous lesson, we talked about how to then take the derivative of the natural log function. So now in the last section of chapter 4, we're now going to finish up by learning how to take the derivative of the natural exponential function. Now, the derivative of the natural exponential function is a little bit unusual. So I'm going to walk you through a simple proof so that we can convince you that this is in fact true. So we have a true statement here. We have the natural log of e to the x is equal to x. We learned this, or we reviewed this, when we went over the properties of logarithms. So we know this to be true. So we're going to start with this true statement, and I'm going to take the derivative of both sides. Now, when I take the derivative of x, that's simple, that's just 1. When I take the derivative of the natural log of e to the x, we know, because we learned this in the previous section, that the derivative of that would be 1 over e to the x times the derivative of e to the x, because there's an inner function. That's using the chain rule. So I have 1 over e to the x times the derivative of e to the x is equal to 1. Now, since we're trying to find what the derivative of e to the x is, I am going to isolate d dx of e to the x. So I'm going to multiply both sides by e to the x so I can get rid of this factor. So when I multiply e to the x on both sides, this fraction cancels, and on this side I have 1 times e to the x, which is just e to the x. So now I'm left with the derivative of e to the x is e to the x. So let's look at the first example. We have find the derivative of f if the function is 8x to the third times e to the x. So what we have here is the product rule. We have 2 factors. Let's look at 8x to the third as the first factor and e to the x as the second factor. So when we use the product rule, we want to take the derivative of the first factor. I bring the 3 down in front. That gives me 24x squared. So that's the derivative of the first factor times the second factor. That's e to the x. Plus the first factor, which is 8x cubed, times the derivative of the second factor. And as we just showed, the derivative of e to the x is e to the x. So that's what we're going to put here for the derivative of our second factor. Now, when we combine and clean this up, we have 24x squared e to the x plus 8x to the third e to the x. I consider this perfectly fine, but the author of the book chose to go a little bit further and factor out what's in common for both of these terms. And it was 8x squared e to the x that was factored out, and then what was left over was 3 plus x. So now looking at example 2, we need to find the equation of the line tangent to the curve f of x, which equals 7x times e to the x at the point 0, 0. The directions also state to make sure that we round to 2 decimal places, so we need to make sure to do that. Now, just like we've done previous functions, we'll follow the same method. First, we want to find the derivative and use it to determine the slope at a specific point. In this case, we're interested in the slope at x equals 0 because the author provided the point 0, 0. So we're going to plug x equals 0 into the derivative to find the slope of the tangent line at 0, 0. And then along with that point 0, 0 that was provided for us, we're going to use that to find the tangent line by plugging all the information into point slope form. So let's begin. Just like the previous example, we have a product of two factors here. We have 7x times x times e to the x. And then, so because we have a product, we're going to use the product rule for derivatives. 7x is going to be the first, e to the x is going to be the second. So according to the product rule, I want to take the derivative of the first factor, which would be just 7, times the second factor, plus the first factor times the derivative of the second factor. Because we have just recently learned that the derivative of e to the x, that's the second factor, is in fact e to the x, that makes things a little bit easier. So we can leave the equation of the derivative as is, or we can factor it and pull out a 7e to the x. That's what both of these terms have in common. But either way, to find the slope now, we got to plug in x is 0 into the derivative. So when we plug in 0, if we use the factored form, we're going to plug in 0 for x. So inside the parentheses, we're going to get 1. Then when we plug in 0 up here in the exponent for e to the x, e to the 0 is 1. So now we have 7 times 1 times 1, which is 7. So that gives us the slope of the tangent line at the point 0, 0. Now, using that point that was given to us, along with our slope, that's 7, we're going to plug that into our point slope form. So y1 and x1 in this case are both 0, 0. Plug in m is 7. So now when I distribute, I get 7 times x, which is 7. 7 times 0 is 0. Y minus 0 is just y. So I'm left with y is equal to 7x. And so here's the graph of 7x times e to the x. That's just in pink here. And when we draw the tangent line of y equals 7x, that's just this line right here that comes up and passes through the point 0, 0 and just touches the graph of 7x e to the x right at that point there. That's in the blue. So now that we have gone through a couple of simple examples with e to the x and finding the derivative, let's get into now what happens when you have an inner function. So the chain rule is going to be used for that. So typically we know that e to the x, when we take the derivative, is e to the x. We just showed that on the first slide. But if we have something other than x, we have to consider using the chain rule. Really, we have to use the chain rule even when it's just e to the x, but when we take the derivative of x, it's just 1, so we don't worry about it as much. So when we find the derivative of e to some exponent that's other than x, we'll call it g of x. When we take the derivative, we're going to get e to the g of x, and then we have to multiply by the derivative of that inner function, which is the derivative of g of x. So let's look at example 3 now. We need to find the derivative of this function e to the power of 3x squared plus 5x. So we know how to take the derivative of e to the x. That's simple, it's just e to the x. But now we have something replacing x. So we have this, what I like to call the inner function. So we're going to use the chain rule here. So when I take the derivative of e to the power of 3x squared plus 5x, we're going to get e to the power of 3x squared plus 5x times the derivative of the exponent. So when I take the derivative of the exponent, I get 6x plus 5, and I have to multiply that by e to the power of 3x squared plus 5x. We should leave the parentheses on here because if we don't, then it might look like only the 5 is being multiplied by the exponential function, when really it's the 6x and the 5 being multiplied. So be careful before you remove any parentheses. Now, looking at this next example, we're going to mix it up a little bit. Notice we have log functions and exponential functions within f of x. So the question is asking us to find the derivative and then evaluate it at 3. And then it says also to round to 4 decimal places. So we need to make sure to do that. So whenever we take the derivative of a log function, it's going to be 1 over whatever that function is on the inside times the derivative of that function. So that's what we're going to start with. So the derivative of this natural log function is 1 over whatever's inside, which is the 2x plus e to the negative 0.05x times the derivative of the inner function. When I take the derivative of the inner function, I get 2 for this term, so I bring that down here. And when we take the derivative of an exponential function, which is what we just learned, it's going to be the same thing, but we also have to multiply by the derivative of the exponent if it's something other than x. In this case, it is. So the derivative of e to the negative 0.05x is going to be e to the negative 0.05x times the derivative of the exponent, which would be negative 0.05. So all of this is the derivative of that inner function, and we have to multiply it by 1 over the inner function. So now, once we get down here and we simplify it, this is what we're going to get. We get 2 minus 0.05 e to the negative 0.05x, because I took this and put it on top because we're multiplying straight across the top. And then on the bottom, when I multiply straight across the bottom, this is a 1 under here, so I get 2x plus e to the negative 0.05x in the denominator. So here's our derivative, but now we still have to evaluate it at x equals 3. So when you put x in as 3 on your calculator, you should get an estimate of 0.2852. And we rounded to 4 places because that's what the directions asked us to do. Now we're going to look at an example of where we need to take the second derivative of an exponential function, which will give us good practice of second derivatives. We haven't looked at that in a bit. So here's our function, e raised to the power of 2x squared plus 5. And this is what we want to take the second derivative of. So we first need to take the first derivative. So because this is an exponential function, when I take the derivative, I just copy this down, and then I have to multiply by the derivative of whatever the exponent is. So the derivative of 2x squared plus 5 is going to be 4x. The 5 disappears because it's a constant, and the 2x squared, the derivative would be 4x. So now we have the exponential function multiplied by 4x, and just because of preference, we bring this in front. Now we have to take the second derivative, but this one's a little bit more tricky because we have to realize that now we need to use the product rule because we have 4x as a factor and we have the exponential function as a factor. So when we go to take the second derivative, we need to take the derivative of the first factor, so the derivative of 4x, which is 4, times the exponential, which is our second factor. And we're going to add that to the first factor times the derivative of the second factor. Now, the derivative of the second factor, that we just took up here, right? This is our second factor, so I can just put this in as the derivative of my second factor. So the author of the book chose to factor out 4e to the 2x squared plus 5, which is fine, but I would be okay once you multiply this out and combine any like terms that there might be, I would be okay with you leaving it like this. So the second derivative is going to be 4e to the 2x squared plus 5 plus 16x squared times e to the 2x squared plus 5. Now this 16x squared comes from this 4x times this 4x when we multiply through and try to clean it up. In example 6, we need to find the derivative of the function f, which is defined as 6e to the negative 7x times the natural log of 4x. We're going to have to use a product rule here because we have two factors. The first factor is 6e to the negative 7x, and the second factor is natural log of 4x. Then we're additionally going to need to use the chain rule because we have something other than x in here, and we have something other than x up here in the exponent. So the product rule says to take the derivative of the first factor. Because this is an exponential function, the derivative is going to be itself, but we also have to remember to multiply by the derivative of the exponent if there's something there other than x, and there is. So the derivative of negative 7x is negative 7. And then, so that's the derivative of the first factor. Here's the multiplication of the second factor. Then I have to add the first factor times the natural log of 4x, that derivative. So when I take the derivative of the natural log, that's going to be 1 over whatever the argument is. In this case, it's 4x. So we have 1 over 4x. And then we have to multiply by the derivative of the argument, which would be 4. Now, this 6 and this negative 7 can multiply to give me a negative 42, and then I carry down the e to the negative 7x times natural log of 4x. Carry down the plus. This 4 and this 4 will drop out. 4 over 4 is 1, and we don't need that. So, and then I have 6 upstairs still, and I have an x downstairs still. And I'm going to carry down the e to the negative 7x. And then if you'd like to go a step further, you can factor out what they all have in common, which is the negative 6e to the negative 7x. And then what's left over is 7 natural log of 4x, and then minus the 1 over x. In example 7, we need to take the derivative and evaluate it at x equals 0. So here is our function. This is going to get lengthy, and we got to pay attention to double negatives here. It's not hard, but we just have to be careful with our double negatives on this one. So to try to make things as simple and basic as possible, I'm going to call this n for the numerator, and then I'm going to call the bottom d for denominator. So before we start getting into this big mess here with the quotient rule, I'm going to first find the derivative of the numerator, and then that way we can just plug it in and not worry about all these extra steps. I'm going to also find the derivative of the denominator. So the derivative of the numerator, I got to take the derivative of e to the x, which we know is e to the x. And then we carry over this minus. And then the derivative of e to the negative x is e to the negative x times the derivative of the exponent, which would be -1. When I put the -1 in front here, that's going to create a double negative, so this is going to be positive. Now, we have the same derivative here, except when I find the derivative of this exponent here to multiply by the e to the -x, when I take the derivative, I just don't have a subtraction here, so I'm not going to have a double negative to change into a plus like I did here. So this is going to be e to the x minus e to the -x. And that is because, again, this was a positive, so I didn't have a double negative, so this remains negative. All right, so now, looking at the quotient rule, we need to take the derivative of the top. That's this. And we got that to be, if we're going to skip these steps here, let's skip those steps. We got the derivative of the top to be e to the x plus e to the -x. That's this here, the n prime. And then we have to multiply that by the denominator. So that's e to the x plus e to the -x. So this is n prime, and this is m. And then we minus the derivative of the bottom. So the derivative of d, that's going to be this. And multiply that by the numerator. So that's this. So now, oh, and don't forget, I almost forgot to say, we have this, the e to the x plus e to the -x squared down here. This is your d squared. Okay, when we start cleaning this up, what we're going to have to do is we're going to have to FOIL. So let me clear this out so we have room. So even though this looks unusual, I know we're used to multiplying polynomials like this, and we haven't done exponentials like this yet, but it follows the same rules. So I'm going to take e to the x times e to the x. Now, when our bases are the same and we multiply, we add the exponents. So that's going to be e to the 2x. Then I'm going to take e to the x times e to the -x. Because my bases are the same and I'm multiplying, I add my exponents. So I get x plus a -x, so that gives me e to the 0. And then the same thing happens when I multiply this. That gives me e to the 0. And then when I multiply, let's see, this times this, that gives me an e to the -2x because I have a -x plus a -x. Now I subtract, and so I have to bring down whatever I get when I multiply this. So make sure that you keep these parentheses around here. You want to multiply everything in here by -1. If you don't keep these parentheses, you're going to forget to do that. Okay, so when we take e to the x times e to the x, that gives me e to the 2x. When I take e to the x times e to the -x, that's going to give me e to the 0. And that's going to be a minus. So we're going to bring down the minus, and everything we get when we multiply this minus or this negative needs to be distributed to all of that. So keep that in mind. So I'm going to repeat the same process. E to the x times e to the x. That gives me e to the 2x because I add my exponents. Then I get e to the x times a negative e to the -x. So that gives me negative e to the 0. Then I take e to the -x times e to the x. That gives me e to the 0. And then last one, I take e to the -x times e to the -x. That's going to give me e to the -2x with a positive because it's a negative times a negative. So then we have to distribute the minus, and then we can also simplify e to the 0 is 1. So this is 1, and this is 1. So that's where they're getting these ones from down here. Let's go. Oh, and don't forget to carry this down because I keep forgetting to mention that since we're so focused on the top, but we still need to make sure that we have d squared down here. When we start cleaning this up, this is where we distribute the negative. So it's going to switch all those signs down here. So now I have e raised to the 2x minus e to the 2x. Those cancel. And then the same thing goes for these. And so what I'm left with is 2 plus 2. So that's 4 on the top. And then, of course, we keep bringing down our denominator squared. Whew, that was rough. It wasn't hard, it was just very tedious. So now we're going to substitute 0 in for x because remember the question was once we find the derivative, we need to evaluate it at 0. So when I plug in x is 0, e to the 0 is 1. So that's going to become a 1. This is going to become a 1. So I have 4 over 2 squared, which is 4 over 4, which simplifies to 1. For the purpose of the interpretation, I'm going to leave it as 1 over 1. And remember, when we're talking about the slope or the rate of change, the change in x is on the bottom, and the change in y is on the top. So this means for every increase of 1, when we're sitting at x equals 0, for every increase of 1, we get an increase of the function by 1. And that is another way to look at it is the slope of the tangent line at x equals 0. Now, this is going to bring us to another rule, although we've already used it, but it's nice to mention it as a formality. So when you take the derivative of e to the ax, so a is just some constant, so for example, e to the 7x or e to the 5x. When we take the derivative, because of the chain rule, this is going to be, the derivative of this is going to be itself, but we multiply by the derivative of the exponent if there's something other than x up there. So when we take the derivative of ax, it's going to be a. So we're going to multiply this by a. So it's another rule to formally introduce. However, we have used it knowing that if there's something up there other than x, we need to use the chain rule. Now, this is going to bring us to another rule, although we've already used it, but it's nice to mention it as a formality. So when you take the derivative of e to the ax, so a is just some constant, so for example, e to the 7x or e to the 5x. When we take the derivative, because of the chain rule, this is going to be, the derivative of this is going to be itself, but we multiply by the derivative of the exponent if there's something other than x up there. So when we take the derivative of ax, it's going to be a. So we're going to multiply this by a. So it's another rule to formally introduce. However, we have used it knowing that if there's something up there other than x, we need to use the chain rule. In this example, we have 3 derivatives that we need to find. The first derivative in part A, we need to find the derivative of e to the 4x. Because this is the natural exponential function, I know that the derivative is itself, but if there's something other than x in the exponent, I need to multiply by the derivative. So the derivative of e to the 4x is e to the 4x times the derivative of the exponent, which would be 4. So we'll just have that as our coefficient in front. Looking at part B, we have to take the derivative of e to the negative 6x. This is again the exponential function, so I know that I can just copy it over because the derivative is itself, but if there is something other than x up in the exponent, we have to use the chain rule and multiply by the derivative of that. So the derivative of the exponent is negative 6, so we'll put that in front and we'll call that the coefficient. So the derivative is negative 6e to the negative 6x. Part C, we have 5e to the negative 0.2x. Again, we're just going to copy this over. So we have 5e to the negative 0.2x, and then we're going to multiply it by the derivative of the exponent, which would be negative 0.2. So that I'm going to put in front here, and I can multiply it by the 5. So I'm going to get negative 1e to the negative 0.2x. And then if you don't want to, you don't have to put that 1 in there. You can just leave it as negative e to the negative 0.2x. In example 9, it states the resale value are in dollars of a particular type of laser cutting tool T years after the initial purchase is approximated by R of T is equal to 450,000 times e to the negative 0.27 T. So we would plug in T, which is the years after purchase, and we would get out the resale value. Find and interpret the rate at which the resale value is changing. So for part A, we need to find the decay rate. Part B, we need to find how it's changing after 1 year. And part C, it's asking how it's changing after 5 years. So because we need to find how it's changing in parts B and C, let's first start off by finding the derivative. Because this is an exponential function, the rule for taking the derivative of an exponential function is that we carry down the exponential function, but then we multiply by the derivative of the exponent. So here's our exponential function that we carry down. So I need to multiply by the derivative of negative 0.27t, which is negative 0.27. So that's here. When we multiply these two values, we now have a coefficient of negative 121,500. Okay, so for part A, it says, from reading the general form of the natural exponential function, A is equal to A naught e to the negative k, the decay rate is negative 0.27, which in percent form is negative 27%. This K is going to be your decay rate. If it was a positive and it was growing, it would be your growth rate. So in part B, it says find the rate when the time that has passed is 1. So we would have to plug in 1 here and use our calculators to come up with an approximation. And that would be negative 92,750.61. Or 61 cents, I should say. So the interpretation is if the number of years since the initial purchase of the laser cutting tool is increased by 1, from 1 to 2, the resale value of the tool can be expected to decrease by approximately $92,750.61. So this would be, if we were doing a tangent line, this would be the slope of the tangent line at 1. So if I made a jump from 1 to 2, where this is sitting at 1, I could use that slope of the tangent line to estimate what we would lose from 1 to 2. So that's what this is saying. Now we're going to do the same thing for 5. If 5 years has passed, then I need to plug in 5 here. And so I plug in 5 for t. And when I use the calculator to approximate that, I get negative $31,497.69. So again, if we were sitting at 5 on this function and we wanted to use the tangent line to approximate what happens if we go from 5 to 6, so that would be an increase of 1. That's where this is coming from. This would be the change in the resale price. In example 10, this is our last example in the lesson. If a person takes a prescribed dose of 5 milligrams of Valium, the amount of Valium in the person's bloodstream at any time can be modeled with the exponential decay function of A of t is equal to 5 times e to the power of negative 0.0144 t, and t is in hours. So we have 3 questions to answer about this. The first question is, how much Valium remains in the person's bloodstream 24 hours after taking a 5 milligram dose? So we start with 5 and 24 hours passes and we want to see what's left in the bloodstream. So for this one, we just need to plug in 5 for t. For part B, it says, how long will it take 5 milligrams to decay to 2.5 milligrams in a person's bloodstream? So in this case, we're looking for the time. So we're trying to find t. If we start with 5 and we end up with 2.5, so we're going to plug in 2.5 for this A and then solve for t. And lastly, for part C, it says, at what rate is the amount of Valium in a person's bloodstream decaying 5 hours after a 5 milligrams dose is taken? Round the rate to 3 decimal places. So because we're asking in part C about the rate that the Valium is changing, that's going to be the derivative. So we need to take the derivative of this function and then evaluate it at 5 hours. All right, so working in part A asks us to find how much of the Valium remains in the bloodstream after 24 hours. So for this, all we have to do is plug in 24 hours for t. So we did that here, and we would be left with approximately 3.5. Now notice, just a quick review, remember we said that the coefficient of the exponential function should always be the initial value. That's your A naught. And notice that up here it says you start with 5 milligrams of Valium, and then after time it decreases. So this verifies, and I just wanted to remind you that this is the initial value. So we go from 5 down to 3.5 milligrams in the bloodstream after 24 hours. Okay, for part B, we're working in reverse. We want to see how long it takes for the initial amount, which is 5 milligrams of Valium, to decay down to 2.5. So because we know that the 2.5 should be what we get out of the function, then we're going to put 2.5 here and solve for t, because it's asking for the time that it takes to go from 5 to 2.5. When we're trying to solve an equation with exponentials and the variable that we're trying to solve for is in the exponent, we're going to use laws of logarithms. But before we use that, we have to make sure that we isolate that exponential. So I'm going to divide both sides by 5. So I have 2.5 over 5. Notice if we reduce that, it would be 1/2, because I have something to point out to you here in a bit. All right, so now that we have the exponential isolated, we can take the natural log of both sides. So on the left side, we have the natural log of 2.5 divided by 5. And on the right side, we're going to have just the exponent. Remember, that was one of the properties that we covered, that if we have the base of the log and the argument is the same and you have an exponent, then when you simplify that, you're just going to get the exponent. because we would use the rules of logarithms to bring the exponent down in front. And then natural log of e is just 1, so we would be left with just the exponent. So now all I have to do is solve for t by dividing both sides by this coefficient. So I'm going to divide both sides by negative 0.0144. And when we do that, we're going to get an approximate time of 48 hours. Now here's what I want to point out. We're trying to go from an initial value of 5 down to 2.5. This is half the amount. So this time right here is actually what's called the half-life. How long does it take for the initial value to be cut in half? And then, so in the next 48 hours, it would be cut in half again. So I would take 2.5, and in 48 hours, it would be 1.25, because you're going to keep cutting that dosage down of what's left in the bloodstream by half every 48 hours. So although that doesn't mention it here, I wanted to point that out. Part C, we are asked to find the rate at which A of t is changing when the time is 5 hours after the Valium has been administered. So we need to find the derivative of this and then plug in 5. When we take the derivative of an exponential function, the derivative is going to be the same, and then you're going to multiply by the derivative of the exponent. So I'm going to take, let's see, 5e to the negative 0.0144t, that gets carried down, and then we multiply by the derivative of negative 0.0144t, which is negative 0.0144. So that's why we have this here. We multiplied by the derivative of the exponent, and when we multiply the 5 and the exponent, the derivative of the exponent, I should say, we get negative 0.072e to the negative 0.0144t. So this is our derivative. Now, if we want to find the rate at which it's decreasing after 5 hours, then we're going to plug in 5 and get that it's decreasing at a negative 0.067 milligrams per hour. Okay, here is our last slide. As usual, try these questions to look back and review and make sure that you understand the main topics after you've completed the homework.